The net electric flux through a closed surface is always equal to zero, and that is something that I'm going to show you in this episode of Physics is Easy with Mr. Jesse. In this tutorial, we're going to calculate the electric flux through closed surfaces. Here is a sample problem, flux through a cube. Consider a uniform electric field oriented in the z direction. Find A, the electric flux through each surface of a cube with edges L oriented as shown in the figure, and B, find the net electric flux. Now let us solve part A, find the electric flux through each side of the cube. So our cube is oriented in a three-dimensional space, and we label this as the y-axis. This is the x-axis, and over here is the z-axis. So let's look at this plane here. This plane, which is the y-x plane. Alright, we have our y-x plane. That is our y-x plane or xy plane, mainly because the plane is composed of the x-axis and the y-axis. Also, we have the x plane, the xy plane here, and we also have another xy plane here. So this is the x-axis and the y-axis. So we also have our xy plane. Now, as far as these planes are concerned, the electric field is actually zero, mainly because the electric field is directed on the x-axis, and no electric field is going to penetrate these two planes here, or our xy planes. No electric field is going to penetrate it. So in fact, if we're going to put that into an equation, the electric field on the xy plane is just equal to zero because of this angle here. It's 90. So remember, theta is between the area vector and the electric field. So if we are going to look at the area vector, so it's actually going to be, it's going to look like this. That's the area vector, and it is perpendicular. So this is our area vector, and it is perpendicular to the electric field. So therefore the angle here is 90. And therefore the electric flux through the xy plane, all right, is equal to zero. So when we say xy plane, we're just referring to the front and back surfaces. Now if we look at the top and down surfaces, so the top surfaces, which is this, and it is our z, and this side here is our x. So this plane here is our xz plane, and also we have another xz plane at the bottom. That's our x-axis. This is our z-axis, no, x-axis rather. Again, this is the z-axis and another x-axis. So we have here our xz plane, which is down, and we have our xz plane, which is top. Also, in these surfaces, electric flux is also zero, because if we are going to draw the area vector of the xz plane, it's going to look like this. This is our area vector, and it is perpendicular with that of the electric field, meaning no electric field would pass or would penetrate through the surfaces. So the electric flux through the xz plane is also equal to zero. Let me just rewrite that down. Electric flux xz plane is equal to electric field multiplied by area cosine of 90 degrees. Again, it's because the angle between the area vector and the electric field is 90, and that is equal to zero, and we're referring to the top and bottom surfaces. Top and bottom surfaces. So having analyzed the electric flux through four surfaces, that is the front and back surface and the top and bottom surfaces, which are both zero, let's look at the two other surfaces of the cube, which is surface 1 and surface 2. So in surface 1, Surface 1 is actually the y, that's the y and the z axis or z surface, so that's the yz surface. And in the yz surface, the area vector is parallel to that of the electric field. So if we're going to draw the area vector for the yz axis, it's going to look like this. And that is parallel, so this is my area vector, that is parallel to the electric field. So in fact, for surface 1, that's surface 1, the electric field is at an angle of 180 degrees with respect to that of the area vector of surface 1. So therefore, our electric flux through surface 1 is just negative EL squared. And why is it EL squared? So again, recall that electric flux is equal to air electric field multiplied by the area, and since this is a cube, the area is just equal to side L, so this length here is L, and this is also L, so L times L, that's our area, cosine, and that's equal to 180, mainly because our electric field points in the opposite, or rather, our area vector points in the opposite direction with that of our electric field. So therefore, cosine is equal to 180. And the cosine of 180 is equal to negative, hence we will have negative EL squared. And this is the electric field for surface 1. Electric field for surface 1. And now looking at surface 2, our surface 2 is just this. So this is our surface 2. It's composed of the y. This is our y. And this is our z plane. So again, this is our yz plane or yz plane. And as far as surface 2 is concerned, the area vector is again parallel to that of the electric field. So the area vector always points outward. It always points outward if we are talking about surfaces or if we're talking about objects that are enclosed. So the area vector points outward. So if we are going to solve for the flux through surface 2, it's the same equation. So that is yz, that's EA cosine theta. Our electric field is just E, and our area, since our surface is a square, so the length of the sides of the square is L times L cosine. Therefore, on our angle this time, since the area vector points in the same direction as that of the electric field, the angle is 0, and therefore our electric field for surface 2 is just EL squared. And this is again the electric field, or electric flux rather, through surface 2. So now that we have solved for all the electric flux through all surfaces, then we could solve for the net electric flux through the entire cube, net or the total electric flux. So therefore, the net electric flux is just equal to the flux through the back surface plus the flux through the front surface plus the flux through the top surface plus the flux through the bottom surface, right? Plus the flux through surface 1 plus the flux through surface 2. And this is just equal to 0 plus the flux through the front surface is 0, the flux through the top surface is 0, plus the flux through the bottom surface is 0, plus the flux through surface 1 is equal to negative EL squared, plus the flux through surface 2, which is positive EL squared, and this will give us 0. So as a matter of fact, the net flux through any closed surface is just equal to 0. Once again, take note that for any closed surface that does not contain a charge, net flux is always 0. So when we say surface, it could be any surface. It could be a cube, it could be a pyramid. So long as the surface does not contain a charge, the net flux is always zero. And that concludes this tutorial. Once again, always remember, physics is easy with Mr. Jesse.